Good evening, everyone. Hello, hello, hello. I appreciate all of you being here tonight. My name is Maria Aschenbrenner, and I use she, her pronouns, and I'm one half of the adult programs team here at the Denver Museum of Nature and Science. Usually, when I'm up here, I am here to tell you about all the cool events that are happening within the next month. And there are so many cool events happening within the next month, but I don't care about that tonight, and don't tell my manager. It is very important to me to thank all of you guys tonight. Tonight is the last 60 Minutes in Space for 2025. I know, and it means so much to me that I see so many repeating faces out in the crowd. So many of you know my name. So many of you, I'm aware of your name. And I am just very thankful for you guys to come out every month and support KaChun, support the museum, and learn something. There's a lot of times in our life where we don't take the opportunity to learn as much as we should, and it means a lot to me and to the science division, I'm sure, that you guys are all out here and you continue to come out, and so I just would like to thank you all. So yes, please. With that being said, I would like to reiterate that today is the last 60 Minutes in Space for 2025. We will start up again January 28th, 2026, which is insane. And I look forward to seeing you all there. And I do have a curiosity question, and I wrote my notes on my phone because I'm really smart. There are two things I want to tell you. Some of you came in through the north and saw that there's something going on over there. If you are a member, there is an 18-plus event tonight to see elephants that you all are invited to go to if you are a member. With that also being said, it closes at 9 p.m., and KaChun will end up his lecture around 8. Q&A goes till about 8:30. So I would recommend, if you want to see that, to not go up later than 8:45 because there'd be no point. You'd have to do a really quick run through. But just want to let you guys know, if you are a member and over the age of 18, you are more than welcome to exit through the north and head up to elephants before you head out. And then, just out of curiosity, KaChun will ask more questions, but how many of you, with a show of hands, have been to all 10 60 Minutes in Space this year alone? Wow. Raise them high and proud. Some of you guys are not proud about being here every month. Big round of applause to you guys. How many of you guys made it between 6 months and 10 months of the year? Wow, another big round of applause to you guys. And then, out of curiosity, how many of you are here for 60 Minutes in Space for the first time ever tonight? Wow, look at all of you guys. So proud of you for coming. That ends my end of year spiel as well. You will not hear from me till January 2026, and who knows, I may be replaced. They might get a cuter, younger version of me. I know they shouldn't. But I will see you all in January. And for the man you're here for tonight, Dr. KaChun Yu, the Curator of Space Sciences. Here's that mic.
All right. Thank you very much, Maria. I actually don't have any questions for you because Maria asked them. Yeah, congratulations for everyone who have been able to make it to most of the, if not all of the 60 Minutes in Space this year. You've actually been to more 60 Minutes in Spaces than I have because I actually missed a few. I was out of town. So yeah, congratulations. So for those of you, can I see hands for people who are here for the first time again? Okay, so wow, a distinct minority. Well, welcome. As Maria said, my name is KaChun, and I am a PhD astronomer here at the museum. And for these 60 Minutes in Space programs, the ones that I do as opposed to the ones done by other people who fill in for me, I tend to concentrate on news stories that really interest me that have popped up over the last month, dealing with astronomy, things outside of our solar system. And for tonight, you'll see a whole wide gamut of stuff, including things that I haven't really talked much about in recent years, but I'll also be going back to some topics that, for those of you who've been to multiple 60 Minutes in Spaces, you'll see that we're returning to some really fun and interesting topics. So with that, without any further ado, let's, Ash, if we can lower the lights a little bit so that it's easier to see the screen, and I'm gonna go ahead and actually the first slide is actually this. This is something that I've been doing for a couple years now, and this is an opportunity for you to ask me a question. And so I'll be showing this QR code again at the end. And I think I said last time that I've accumulated so many questions that I'm going to be retired by the time we go through the current set of questions. By then, we'll probably have 100 times as many. But I'm going to try and go through at least a couple questions that were submitted by people out in the audience, and we'll see those answered at the very end. So let's go to the first topic, which is we're going to look at some pretty pictures, and we're going to look at a lot of images from the James Webb Space Telescope. But first of all, we're going to actually look at images taken from other observatories and telescopes. And so we're going to concentrate on the galactic center. So this is the center of our own Milky Way galaxy. Many of you are aware that we live in a galaxy consisting of a couple 100 billion stars. We live in a spiral galaxy, so you can think of like a big flat disk, like a pizza or a pancake, and the center of the galaxy is in the middle of that pizza pie. And our sun orbits in the disk, or in the pie, about halfway from the center to the edge. And if we look towards the center of the galaxy, we see sort of a plane, and that corresponds to the disk. And these observations are in the submillimeter, which is similar to radio, and also in the mid-infrared. And so you'll see lots of gas clouds. That's what this orange material is. They correspond to the glow from gas and dust. And we're going to zoom into a gas cloud called Sagittarius B2. And so you see that it's not quite at the galactic center, but it's pretty close. And at these, so these are degrees in the sky. And so this gas cloud is only a couple hundred light years from the very, very center of our galaxy, which we know at the very galactic center, we have a supermassive black hole, about 4 million times the mass of our sun. And we'll be talking about black holes a little bit more. And so here we're looking at the galactic center again, but we're looking in images taken from ground-based telescopes, looking at optical light. So this is the same sort of light that our eyes are sensitive to. And you might notice that this looks very different. You see the glow from stars, and there are some nebulae which are lit up from massive stars, but you also see lots of dark material, and that's because, again, we're seeing gas clouds, but in optical or visible light, these gas clouds look very dark because they block the light of stars from behind them. And so you probably expect we won't see very much if we stick to visible light. So what I'm going to do now is we're going to switch to the infrared. And so this is a survey taken from a telescope actually in Western Massachusetts, run by the University of Massachusetts Amherst. And this is in what we call the near infrared, so it's actually pretty close to the optical wavelengths of light. And so again, you can see lots of gas clouds, you can see the disk of the Milky Way, and we're just going to zoom in. And then actually the very center of the Milky Way is where this red arrow is pointing. So we're going in towards the B2 cloud, and we're going to zoom in again. And this particular cloud is of interest to people who study the galactic center, just because even though it's not a very massive cloud, it contains about 10% of the mass of all the gas and dust that is circling the center of our galaxy. It's responsible for about 50% of the star formation. So we know that gas clouds, these massive clouds full of gas and dust, are the sites for star formation, where parts of the cloud can collapse to form stars. And we're now, I'm going to go ahead and look at this gas cloud taken by the James Webb Space Telescope. And I'm actually not sure which part of the previous image we're looking at, because Webb, looks at a very, very tiny patch of the sky, and the orientation might be completely different. So I didn't take the opportunity to try and figure out where we are. But you can see just how many stars show up in the infrared. And this is from the NIRCam, which is the near infrared camera. And then there's also there's a mid-infrared camera as well. And if I flip back and forth between these, you can sort of see corresponding objects showing up in these two different sets of wavelengths. And we see a lot of dark spaces, and especially over here. But there are the reason why. Well, let's see. We are still seeing some of the dark gas clouds, and those are the regions that are black or dark in these images, because there are so many stars in towards the center of our galaxy that you would actually expect this to be completely filled uniformly by stars, but because there are still gas clouds that are dense enough, dark enough that the infrared light still can't go through, we're actually seeing evidence of some of those clouds. And so these beautiful images have been released, but there actually haven't been any scientific papers that have been released discussing what sort of science can be learned from this. But NASA also released these annotated images that show you the wavelengths that were involved in observing this region. And so you can see that in this case there are 2, 4, 6, 8, about a dozen different wave bands where they use different filters to look at specific colors in the infrared, and those colors were then combined into sort of deep blue, light blue, green, yellow, orange, and red to form these nice composites. And the reason why they do this, and in the mid-infrared they only had 3 different colors, one for red, green, and blue, but these different colors, these different filters sample different wavelengths, and those wavelengths correspond to different molecules, different atomic species that might be emitting in those different bands. And so by looking at multiple wavelengths, you can hopefully get a good idea of what is happening physics-wise in this region. And so future studies of this region will be diving really deeply into the specific wavelengths that we're seeing. All right, so that I'm going to, since we've been talking about star formation, and stars, we know when they form, they often form with planets. I'm going to also go and switch it up to talking about ocean worlds, or talking about ocean worlds very briefly. And so for those of you who've been to multiple 60 Minutes in Spaces, including back in May and September, and also back in 2020, and those are the obvious ones. I think I've probably talked about them even more often. But the ocean worlds are these planets that are larger than our Earth. Another term for them is super Earth. They're typically 2 to 4 times the diameter of our Earth. Another term for them are sub-Neptunes, because they're smaller than Neptunes. So they're basically between the Earth and Neptune in size. And the idea is that we've found evidence for these worlds that are halfway in between the Earth and Neptune. And in our solar system, there's really nothing that corresponds to a super Earth or a sub-Neptune. You go from Earth size or Venus size to Uranus and Neptune, which are about the same size, about 4 times the diameter of the Earth, and there's nothing that's halfway in between. But it turns out that when we look at planets outside of our solar system, the vast majority, or there's more super Earths / sub-Neptunes than there are any other category of planets. So, so a lot of people concentrate their attention to these super Earths or sub-Neptunes, and so theoretically, astronomers think that there's a good possibility that a lot of these are ocean worlds, or worlds where a lot of water ice is accreted, and so you have worlds that have far more water, meaning oceans that could be hundreds of kilometers deep, whereas on our planet, our oceans are no more than 10 kilometers deep or so. And or they might also have these very thick hydrogen atmospheres. But a paper came out just recently where they suggest that instead of thinking of water worlds or water ocean planets, we should be thinking of soot worlds instead. And by soot, what they mean is not necessarily the soot that you find in your chimney or your fireplace, but by soot they mean what they call refractory carbonaceous materials. And these are materials that consist of carbon, hydrogen, oxygen, and nitrogen, or CHON, CHON. And by refractory, that means these materials are not easy to break down or decompose into smaller bits. And so they tend to accumulate. And the reason why they suggest this is that because these materials will remain solid up to about 500 degrees Kelvin, which is more than 200 degrees Celsius, so twice the boiling point of water. What this means is that if the nebula, the cloud that collapses into your solar system, contains a lot of these sooty materials, they will likely remain even after they've accreted onto your planet. And so in this paper, they provide this diagram that talks about the soot line, which is over here, and the ice line. And what these lines correspond to are regions where ice and soot might exist. And so if you imagine there's this big cloud that's collapsing into a star, and there's an accretion disk where material is funneling towards the star, and it's also forming planets. What happens is that the star is heating up this disk, and so it's really hot close in to the star, and as you get further and further out, it gets cooler and cooler. Well, if the temperature is greater than 500 degrees Kelvin, what that means is that there's no water ice, no soot that can accrete onto the planets because all of that material remains vaporized. It's basically in a gaseous form. And so the only stuff that can accrete are the solid, rocky, metallic materials. And so you basically get rocky planets inside the soot line. But between the soot line and the ice line, it's basically cool enough for soot to remain as sooty materials. And so now you get planets that are a mix of rock and soot. And then finally, if you get even further out, where it gets cold enough for water ice to exist in a solid form, then what gets accreted is a combination of all three. You get the rocks, the metals, and the sooty materials, and the water ice. And so they run simulations of this, and this simulation is where the planet is actually consists of multiple layers, meaning you might have a core that's metallic in the very center, you might have a silicate mantle surrounding that metallic core, and then you have a sooty layer above that, and then maybe a water ice layer above that. And then the single layer models occur where you mix up all the materials, and so you don't have this stratified planet. And what's plotted here, this is a really complicated plot, but we have mass of the planet along the bottom, and it's in terms of Earth masses. So this is 2 times the Earth's mass, 4 times, 6 times, all the way to 10 times. And then along here is the size of the planet, the radius. And so what this means is that when they run their computer simulations, they find that rocky planets, meaning worlds that are just rock and metal, they tend to fall along this line. And then if you have a planet that is just soot, it falls, well, soot and rock, it's going to fall along this gray band. And then in this interesting case, if you have a soot and water world versus a soot and let's see, soot water. Well, they have 2 different types of soot and water worlds, but they tend to fall along here. But the other interesting thing is that this kind of weird dash line is rock and water, so it basically overlaps with the soot and water world. So what that means is that if these soot worlds exist, there's really no way to distinguish between them and a rock and water world based on our current sets of observations. And so, so these researchers are proposing this new class of planet that astronomers hadn't thought of before. So this is actually really exciting, but it also says that we perhaps can't distinguish, at least if we can measure the masses and the sizes of these planets, we can't really tell whether they're necessarily rocky and watery, or they have some combination of soot as well. And so, this is the first paper involving these sooty worlds, and hopefully this will kind of spur other groups to really dive into this and to run their own simulations and models. But what's also really interesting is that, we think, well, these sooty worlds might be really exotic, but what they really mean is that there's a lot of carbon, organic carbon compounds in the surface of these worlds, and there are actually worlds in our own solar system that are like that. So the moon Titan, which orbits Saturn, has a lot of organic compounds on it, and so we think that the atmosphere is full of these methane and ethane and these other, and the surface is also full of materials that we think of as carbonaceous. And so this is simply just taking this example of Titan and expanding it into these super Earth planets. So we'll see where this research goes in the future. All right, I'm going to continue talking about planet formation, and to do that, we're going to talk about this object HH211, which was observed by the James Webb Space Telescope. And what we're looking at is actually a very young star with a solar system that's forming, and it's right in the middle, right here, where you can't see anything. And the reason that you can't see anything is because it's the light from that star is being blocked by the accretion disk, by the material that's fallen in, and that material is accreting onto the star and is forming or will form planets. But what's also really weird is that this young protostar is emitting a pair of jets that are shooting out from that star, and it's plowing into the gas that surrounds the accreting star, and you can see the jets coming out, and it even looks like the jet is carving out like a cavity. I mean, you can sort of see this looks like a cocoon on either side, and there's also this brilliant emission that's colored red in this image, and that's due to the jet plowing into the interstellar gas that's surrounding the star. And so it's creating these bow shocks. You can sort of see these angular, triangular shaped regions, and you can even see that it's symmetric, meaning this gas here or this jet here corresponds to that jet there, and some of these bow shocks also correspond to each other. So there's definitely things going on that sort of makes sense in the sense that it's symmetric, but why would there be a jet, or why would jets be shooting out of these young stars? Well, we're going to talk about that, but before we do that, I'm going to talk about what HH objects are. And HH is actually short for Herbig-Haro, and so these Herbig-Haro objects have actually been known since the 1940s. So Herbig-Haro, they actually represent George Herbig, who's an American astronomer, and Guillermo Haro, who's a Mexican astronomer. And so they were observing, and back then you observed with glass photographic plates. And so this is an example of one of those plates where instead of having computers where you can add annotations digitally, these are all handwritten in ink. And this is a negative, meaning what we're seeing, everything that's bright is actually black, and everything that's black is emitting light. And so these Herbig-Haro objects, or HH objects, were basically stuff that these astronomers noticed on their photographic plates, and they didn't look like stars because stars show up as single points. But what they looked like were just these weird fuzzy patches that were somewhat irregular. So here's HH1 that definitely looks kind of irregular. HH2 has a bunch of different components that are labeled A, B, C, D, E, F, G, H, I, and L, I think. And then there's also HH3. And so over the years, so this was actually independently discovered by the two of them, and they met up at an American Astronomical Society meeting in Tucson, Arizona in December of 1949, and realized, after talking to each other, that they were finding the same sort of things in the sky. And so it was a big mystery as to what these were. But over time, what astronomers realized is that these are, they're not stars, but they do show up in regions where we see a lot of young stars. And so what these Herbig-Haro objects are is basically shocked gas that's at high velocities. It's gas that's moving at supersonic velocities, and it's hitting other gas in the gas cloud. And you can see that there are stars. These individual dots are stars, but there aren't that many stars, and that's because we're actually in a region where there is a big molecular cloud. So there's molecular gas with lots of gas and dust that obscures the starlight of stars in the background, so we don't see very many stars. And so these HH objects tend to be in regions where there's a lot of gas. And so they seem to be associated with star formation. And what people realized is that they are evidence of those jets that we saw in the last slide. And so when you have these jets plowing into molecular gas, you can the emission, the light that is emitted, shows up as these HH objects. So the HH211 object that we saw the James Webb picture of is actually located in this gas cloud called IC348. So there are a bunch of gas clouds in the constellation of Perseus, and all these clouds are about 1,000 light years away. And so because they're relatively close, astronomers have spent a lot of time studying these clouds, looking for young stars and looking for signs of star formation. And I've actually observed in this area in the past myself. But we're going to zoom into IC348. And so when you look at it, this is the region where there are lots of young stars that have formed. This bright star is actually Alpha Persei, so it's actually completely unrelated to these young stars. It just happens to be in the foreground. And HH211 is down here. Okay, so we're actually, the center of the cloud is kind of in the center of the image. And this particular object wasn't discovered until 1994, so just over 30 years ago. And by then, astronomers were observing in the near-infrared, and so that's how a lot of HH objects are discovered, not in the optical, because it's hard to see things when they're obscured by the gas in visible light. But in the infrared, you can peer through a lot of that obscuration. So this is the discovery image, and here's a more recent image. I mean, it's still from the early 2000s, and you can see that HH211 jet, but there's also another jet coming from another protostar over here. And so this region is just rife with lots of star formation. And as far as what exactly is happening, this is kind of a cartoon showing how stars form. And so we have a gas cloud, and then as parts of the cloud become unstable and collapse to form stars, you have gas flowing in and falling towards the center of regions that will eventually become a protostar, and the gas piles up in an accretion disk, and much of that, or some of that gas falls into the main star at the center, and most of the gas actually gets ejected in these jets. And so over time, what happens is not only does the gas funnel into the star, and the gas in the accretion disk form the planets. But the jets actually clear the surrounding cloud. And so we think that star formation is actually self-limiting, so that not all the gas can fall in because these jets basically disrupt the cloud. You have this cloud that surrounds this protostar, but over time, the jets and the winds from this and other young stars basically destroy the cloud from the inside out. And so star formation, so we think that, for a typical molecular cloud, perhaps no more than about 5% of the mass actually ends up in new stars. So the big question is, why do these jets form? And this is something that astronomers have grappled with for decades, because they started seeing evidence for these jets just from the shocked emission, the Herbig-Haro objects, going all the way back to the 1940s and 1950s. And people didn't really quite understand what they were until they started doing spectroscopy in the 60s and 70s. But it was clear that there was stuff happening, and there's a lot of activity in these clouds. And so a big question is how do jets actually launch from the protostars? And there have been a lot of theories over the last 30 or 40 years, but one of the prominent theories is something called the X-wind. And basically the idea is that you have a star at the center, and you also have an accretion disk. And it turns out that these stars tend to have really strong magnetic fields. So the younger the star, the more active it is, the stronger the magnetic field. And the magnetic field can actually interact with the accretion disk because when you have a field that's very strong, the gas that collects due to that field at a certain point has the same density as the gas coming in to the accretion disk. And so that's the edge of the accretion disk, which is truncated by the magnetic field. It becomes kind of an interesting place where lots of things can happen. And so this X-wind theory was proposed originally by Frank Hsu, who is an astronomer at Berkeley. And he and his colleagues worked on refining this model over many, many years, and other people also worked on it. But basically the idea is that because of interactions between the field and the star and the accretion disk, you basically have these field lines that originate at the edge of the disk that come out in an X-like pattern, and hence that's why they call it an X-wind. And so you have field lines that go out, and as the star rotates with the field, and the gas in the accretion disk is also orbiting, and so they tend to orbit pretty much very similar velocities at that region. And what happens is a lot of the accretion disk gas gets funneled out along these magnetic field lines, and they end up going along the north and south poles, very similar to what you would expect, when we see these jets. And so now we're finally ready to go back and talk about the James Webb observations. And so this is a paper that just came out by Qinfei Li, who is a star formation researcher based in Taiwan. And he used James Webb observations as well as radio telescope observations from the ALMA radio array. And the ALMA array gives you very high resolution radio observations. And so this is a figure from their paper. So this is sort of what we saw in that first image. And what we're seeing are the infrared emission as observed by the James Webb Space Telescope. So in the infrared, the accretion disk, the infalling gas envelope, still is so thick that it obscures the infrared light. But you can still see the jet coming out. It's super collimated, meaning it's really tight down close in to the protostar. But as it plows into the surrounding gas, you can see it gets really, it gets bigger. It creates these bow shocks, and it gets really complicated looking. And then what we're going to do is we're going to zoom in to just the center box. That's what these dashed lines are. And so when we zoom in, the red is still the infrared emission, but the green now is radio observations from the ALMA array. And so this middle plot shows silicon oxide, SiO, and then this shows carbon monoxide, CO. Now you might remember, most of the gas in the universe is actually hydrogen. It's the most common element. So why are astronomers observing in these weird species? Well, it turns out that in radio astronomy, hydrogen gas is actually very difficult to observe, especially when it's cold. And so you have to go and look at other tracers that are much rarer than hydrogen, but they show up, they emit light more readily. And so that's why we're looking at silicon oxide and carbon monoxide. And so at least here, we don't quite see, you can, for those of you in the front, you can see that there's actually still a gap. It looks black in the SiO, and it's also sort of the case in the carbon monoxide, but there's definitely more carbon monoxide emission going all the way to that accretion disk than the SiO. And the researchers think that the silicon oxide is tracing internal shocks. So basically what's happening is that there's velocity differences as the gas is getting ejected out. Sometimes it's getting ejected out quickly, other times it's getting ejected out slowly. And so different parcels of gas moving at different speeds collide, and they create shocks, and those shocks are seen in the silicon oxide emission, whereas this flow in the CO seems to be a lot smoother. And what they do is they create an X-wind model. So not exactly the one that we saw earlier, because the models have been refined over time, but their model has the accretion disk, and they still have these field lines where the gas flows out. And this is kind of a 3D mock-up of it, where there's the orange glow represents how much gas is flowing, but the greenish blue represents the strength of the magnetic field, because it turns out that magnetic fields are really important in defining the X-wind. And then here are the results. So the messy looking images are the actual data. So this is what the jet looks like in the radio observations, and then this is their beautiful, perfect modeled jet from their simulation. But you can see that more or less looks similar. And then these two other plots actually are showing the velocity of the gases. And so they're basically showing that the messy gray scale observations are roughly matched by the perfect red contours from the model. So the model more or less describes or matches what's observed. So this is probably the first time that we've had such amazing observations from a telescope like James Webb and ALMA, where you can use those observations to sort of constrain an X-wind model and actually show evidence that the X-wind is viable in explaining how these winds are launched, or these jets are launched from these young protostars. So after people coming up with X-wind theory for 30, 40 years, we finally have observations that can show us that the theory seems to be correct. All right, we're going to go from protostar jets to another type of jet. This one is a jet coming from the giant elliptical galaxy M87. This galaxy is in the Virgo supercluster, so it's about more than 50 million light years away. And the jet, in this case, comes not from a young star, but from the supermassive black hole at the center of this galaxy. So whereas our galaxy has a supermassive black hole that's only 4 million times the size of our sun, M87 has a supermassive black hole that's 6.5 billion times the mass of our sun. So it's absolutely ginormous. And and there was just a paper that literally came out a couple weeks ago where they again used JWST, James Webb Space Telescope, to observe the M87 jet. And this is a jet that has been observed in the radio. It's been observed by optical visible light telescopes, but it's been hard to observe just because there's a lot of contamination from the stars in the galaxy. And so what they did was they actually modeled the stars. So here is the raw observations, and they created a model of what the stellar population must be like. And they subtracted the stars, and they got this. And so you can see this, it's really noisy, but it more or less has removed most of the stars, or the effect of the stars, and you have the jet kind of left by itself. And then they isolate the jet in that far image to the right. And here is what they see. And again, this matches all of the observations that have been done previously at other wavelengths in radio and in the optical. And most of these blobs were first observed, in the radio, but some of them, like HST1, this blob over here, so this box is zoom in to that smaller white box, and the circle represents the location of the supermassive black hole. So we don't see any emission immediately from around the black hole. But you can see that the jet isn't completely straight. It appears to be kinked. And in fact, that might even have to do with magnetic fields in the jet. And here we're actually just looking at different wavelengths. So these are all of the wavelengths that were observed by with James Webb. And what's also interesting is that they were able to see the counterjet. So now, for those of you who are familiar with M87, you've probably always seen this weird kink jet, but you might not have even been aware that. We know that there probably is a counterjet, but I wasn't even aware that it's been observed, and that's only and it's not as bright, probably because there isn't as much material on this other side of the galaxy for it to run into. But it was observed in the infrared, and here is what it looks like at the 4 different wavelengths that where it was observed. So you can see the counterjet where it runs into whatever gas is on the other side of the galaxy. Looks sort of like a C shape, and there is some emission in the shorter wavelengths, but it doesn't really show up until we go into the longer wavelengths. And here is what the M87 jet looks like in radio observations. So this was taken by the VLA observatory down in New Mexico, the giant array of 27 radio telescopes. So here again is that main jet. M87 is somewhere in the middle there, or the supermassive black hole is somewhere in the middle there. And you can see in the radio, the counterjet really shows up. It really pops. So I think, the paper where I'm gathering all these images from, they don't really go that much more into what they see other than describing these features and what it corresponds to. And other than showing that they were able to get infrared observations of this jet. But I do find it really interesting that a lot of we have very different phenomenon. Star formation in one case, where stuff is flowing into a young star that's accreting, and in this case we have a supermassive black hole where stuff is falling in, but there's also an accretion disk. But in both of these cases, you have jets being formed. And because black holes are very different from young stars, the mechanisms might be somewhat similar, but they're very different. And in the case of black holes, the jets are formed via something known as the Blandford-Znajek process. I have no idea if I'm pronouncing that second name correctly, but this is a process that they figured out back in the late 1960s. And again, and I don't have the time nor the expertise to really describe what's happening, but again, the idea has to do with magnetic fields. And in this case, the magnetic field is threaded throughout the accretion disk. And so it's that interaction of the magnetic field with the black hole that can actually extract energy and momentum that allows gas to be shot out along the directions of the jet. So, it's interesting that in astrophysics, you can have somewhat similar but very different phenomena arise, and they leave you with results that look somewhat similar at vastly different scales. So here we're seeing a jet that stretches 5,000 light years, whereas the protostellar jets might stretch only a few light years at most. All right, and I'm going to end with a topic that I've talked about before, and it has to do with the Dark Energy Spectroscopic Instrument, or DESI. And there was a huge tranche of papers that was just released, and they had to do with a new release of data from this observatory, or not really observatory, but this survey. This is a survey done at a particular telescope, and the one paper that I'll be talking about amongst multiple papers that were published, here is the first page of it. And so you can see, there's, I'm guessing about 160 or 180 authors. I didn't actually do a count. And then here's the second page, and then the third page, and then finally the fourth page, where we list all the different institutions and affiliations of all the authors, and then finally we get to the abstract, and then where the paper really starts. So, this is a huge collaboration with hundreds of astronomers and engineers and technical support staff, all working on this one particular instrument, DESI. And as the name suggests, it has to do with dark energy. So what is dark energy? Well, dark energy makes up most of the universe. We know from Einstein that matter and energy are equivalent, but over the last half century, we've realized that there's a lot that we don't understand about our own universe. And that primarily has to do with the fact that the ordinary matter that we're familiar with, things made up of atoms, with protons and neutrons and electrons, basically everything in this room that we can see, that makes up only a sliver of our universe. So basically less than 5% of our universe consists of ordinary matter. A quarter of the universe, about 26%, is made up of dark matter, which a lot of people have a lot of ideas and speculations of what dark matter could be, but we still don't really know what dark matter is. And then more disturbing is the fact that almost 70% of the universe is made up of this mysterious dark energy, and we really have no idea what dark energy is. Again, there are lots of theorists, physicists, cosmologists who have their own pet ideas and theories, but they're even even more out there than the dark matter, because there's less to constrain our understanding of dark energy. Dark energy was really only discovered in 1997-98, when observations of distant supernova suggest that the universe is expanding faster than we thought it should. And basically, to understand that, if you think about the universe expanding after the Big Bang, it's filled with matter and energy, and matter and energy has a gravitational pull. And so what you would expect is, if the universe was expanding, it should slow in its expansion. Just like if I had my keys and I threw it up, as the universe pulls on itself, it should cause the expansion to slow, and then perhaps if there's enough matter and energy, it would even cause it to slow to a stop, and then it would recollapse. And so that was the idea for how this might work, but the discovery of dark energy kind of overturned that completely, because dark energy is this mysterious property of space itself that causes space-time to basically expand faster. And so if he had a certain amount of, and if dark energy was constant, meaning it didn't change over time, and up until recently, we thought that the evidence did show that dark energy was constant. What that meant is that because there's a certain amount of dark energy in space itself, if there's a certain amount of space in between a galaxy, and you double that volume of space because the galaxies have moved apart, the amount of dark energy has also doubled because your volume of space has doubled and the amount of dark energy in that space has doubled. And since dark energy tends to push things apart or push space apart, now there's more dark energy to push things apart even more. And so with constant dark energy, you would expect the universe to basically accelerate and expand faster and faster. And so after the discovery of dark energy, people were postulating, well, instead of the universe slowing to a halt and then recollapsing, it's likely that the universe would just continue to expand faster and faster. The galaxies will run away from each other. And if you live hundreds of billions of years, tens of billions of years in the future, you'll see fewer galaxies because they're further away, they're dimmer, and perhaps far enough in the future, you won't see any galaxies at all, or other galaxies at all, because they've expanded so far away that we can't see them anymore. So that was sort of this speculation that was happening, and astronomers, cosmologists built up this idea of this standard model of cosmology where the fraction of matter, and dark energy is what we see here, and where dark energy is constant. So in order to really understand whether dark energy is constant or not, you need to be able to probe the universe at different points in time or different distances, because we know, the further back and the further away you look, you're actually looking further back in time, and to try and determine, whether the galaxies are indeed moving faster apart from each other. But that's kind of hard to do because there isn't a bunch of yardsticks or rulers out in space that tells you, how big something that volume of space is. Well, it turns out that there is something, and it's something called baryon acoustic oscillations. And for those of you who've been to many 60 Minutes in Spaces, you might have heard me talk about this. But the basic idea is that very early on in the universe, before things cooled off and protons and neutrons and electrons combined, or actually to form ordinary matter, you basically had the matter, the particles in a soup with the photons, the electromagnetic radiation, because it was so hot that the individual particles couldn't form atoms. And so this fluid of photons and baryons, the protons, basically responded together. And sometimes you might have regions that were slightly overdense than others. And when you have charged particles, they tend to bounce off of each other. And so if you have a slight overdensity of charged particles, they would bounce off of each other, and they would create what are effectively sound waves, these pressure waves that would propagate out. And so that's what this visualization is showing, how these pressure waves expand outwards from these slight overdensities. But as the universe expanded, at a certain point, it cooled enough for the protons to combine with the electrons, and they formed the first atoms, the first hydrogen atoms, and a smidgen of more complicated or heavier atoms. And when that happened, you didn't have the heavy baryons, the particles bouncing off each other. They would just slide right past of each other. And so whatever overdensities that were appearing in these sound waves that were propagating outwards, they basically froze in place as the universe cooled. And so this basically represented these structures which, once they froze, they continued to expand with the universe. And as the universe grew larger, they also grew larger along with the universe. But these basically represented sort of like a yardstick that you can use to measure the universe, because these the size of these baryon acoustic oscillations, or BAOs, basically could be represented based on just a few parameters that depended on the parameters in the early universe, like the density of the gas, and so forth. So if you were able to measure these baryon acoustic oscillations, then you could actually be able to measure how fast the universe is expanding, because different baryonic acoustic oscillations would appear at different sizes depending on where they were in the universe, very early on versus later. And so astronomers have been interested in observing these BAOs. And in order to do that, you need to have lots and lots of observations of galaxies, because you're basically looking for slight overdensities in the galaxies in space, and you would want to be able to do it very far into, be able to observe this in the very distant universe, which, because the speed of light is constant, when you look at things that are very far away, you're also looking backwards in time. So you want to be able to see very deeply into the universe and see lots of galaxies. And so in order to do that, you need to have a dedicated telescope, or at least a dedicated survey that can observe these galaxies. And let's see, they did this at Kitt Observatory down in southern Arizona. And the DESI instrument was basically just attached to a large telescope there. And they were able to observe these galaxies by using basically robots that would position detectors. So they knew where the galaxies were in the sky. And every time they moved the telescope to observe a different patch of sky and a different group of telescopes, these robots would move these fiber optics to exactly where the to each galaxy would be. And then they would be able to take a spectrum of each of these galaxies. And from the spectrum, you can get information about how fast it's moving and infer how far away that galaxy is. And so we're going to see an animation, and some of you may have seen this in past 60 Minutes in Spaces, but this is an animation showing how the DESI instrument basically observes the entire sky. So we've unflattened the sky. We see the Milky Way, our own galaxy, and we need to observe away from the plane of the Milky Way to see other galaxies. And so you see all the regions of the sky that it's observed. And so it's covering a good fraction of the northern and part of the southern sky. It obviously can't observe galaxies where the Milky Way is, because it's going to obscure our results. And so this animation from Fisk Observatory in Boulder, on the CU Boulder campus, they created this. And unfortunately, YouTube compresses the images or the video, so at times it'll look really blocky. So, but this is just a fly-through of, at this point, this might be only 14 million galaxies. With the second data release, which just came out, they're up to 15 million galaxies, and the survey is supposed to run for another 2 years, and by the end, they hope to have about 40 million galaxies observed. And so that gives you an idea of what all those galaxies look like. And so you can see that they're not uniformly spread out in space. They're actually clumped into clusters and superclusters, and even the superclusters tend to be along the edges of these gigantic bubbles. And you might have gotten a sense of that as you're watching the animation. I don't know how much longer this is going to run through. Oh, it keeps going. We're running out of time, so I'm going to go forward. All right, so let's go back to this paper with over 100 authors. And if we look at the title, it's about measurement of baryon acoustic oscillations and what it means for cosmological parameters. And so what they did, so this plot shows kind of the history of the universe. So we started at the Big Bang here, and then we go to the present off to the right, and the size of the universe is, plotted along the side here. So basically, the universe starts at 0 size and gets bigger and bigger. And what they did was they looked at different classes of galaxies. And so you can see that astronomers have identified different groups of galaxies that show up at these different distances or redshifts. And when they look at certain bins of galaxies that are identified by those different colors and by those different categories, they try to look for baryon acoustic oscillations within each of these bins. And the basic results for dark energy, I mean, they've released a bunch of papers and they look at a lot of different results. But if you are interested in just dark energy, this is the critical plot. And again, this is a very confusing plot, so I'm going to have to try and explain what it means. So along the bottom here is the different values of dark energy today. And so that's what W0 is. And along the side is the value of dark energy over time, over the history of the universe. And if you assume that dark energy doesn't change over time, meaning it's completely static, you would expect your results to be at that point where the star is, where WA is 0 and W0 is -1. So you follow -1 up and 0 up there, that's where the star is. But as you can see, the data, the observations, do not really overlap with that where that star is. Instead, depending on which data sets that you use, and so these plots basically show DESI combined with other surveys, other data sets. The range of values for dark energy is actually along those different ellipses. And so the overall takeaway is that the models that explain the observations, you basically have to assume that how dark energy behaves today has to be greater than -1, and how dark energy behaved in the past has to be less than 0. And again, that's meaningless to everyone in the audience. It's kind of meaningless to me. But the takeaway, if you look at the results of this paper, is that dark energy is evolving over time, so that it's changing. It's not static. It's not fixed. And the way that it's changing implies that the strength of dark energy is actually lessening. So and what that implies is that instead of the universe expanding faster and faster, because the more space you create between the galaxies, the more dark energy there is, and it pushes the galaxies apart even faster. Actually, I have one other slide. For those of you who were at the April 2025 60 Minutes in Space, this is what the result was in the paper from the original data release. And but again, what this implies is that that picture of how dark energy causes the universe to expand faster and faster is no longer correct, and that has people writing papers about talking about the lifespan of our universe. So this was a paper that's not been peer reviewed yet, but it showed up in one of the servers that where people can deposit papers that are under review. And if you look at the abstract really closely, you can see what the conclusion is. This negative lambda, and lambda stands for dark energy. The negative dark energy leads the universe to end in a big crunch. Using the best fit values of the model as a benchmark, we find the lifespan of our universe to be 33 billion years. So, and now this, conclusion depends on all these suppositions that these authors have. So for this particular paper, the authors have their own pet theory about how dark energy evolves, because they have an idea for a particle that causes dark energy. And so when they run the results of this particular model for their dark energy, they suggest that the universe will slow down and then basically fall back on itself in another 20 billion years. So we come back to this, and this is probably, it's a confirmation of the earlier result that we saw in April, but it's actually really exciting because astronomy and really all sciences rely on new observations. So for a long time, our observations weren't good enough to tell us whether dark energy was unchanging or whether it changed. And if you didn't have any better observations, a very good assumption would be that dark energy was constant. But now we're getting more and more solid evidence that dark energy is not constant. And so I think that is really exciting news because that means we'll have a really better understanding in the next few years about where our universe is going. And I know we're running out of time, so maybe perhaps we'll save this for the discussion or in the Q&A. But I said that I would bring up two questions from previous audience members, and they are: what's our best theory for what happened before the Big Bang, and what is the possibility of the multiverse? And it turns out that my ideas about the answers to these questions do sort of relate to what we just talked about. But since it's after 8 and it's a school night, I'm going to stop it right there. And for those of you who need to leave, feel free to leave. I mean, you might want to go see the elephants exhibit upstairs if you're a member. But for those of you who want to stay and hear me expand on this, feel free to. And I'll be happy to talk a little bit more about this and also answer your other questions. So thanks, everyone. So before I jump into answering these two questions, does someone have like a super burning question that they think they can't absolutely wait to be answered before I move forward? Okay, maybe one really quick question that I'll answer before I... Say that again? Is there any commotion when galaxies merge? Yes, there can be a lot of commotion. So, even though the universe is expanding and we think galaxies are flying apart, well, it turns out that gravity is actually still really important in helping us define what galaxies and clusters of galaxies look like. So galaxies tend not to be just by themselves, but they tend to be in clusters, and those clusters are bound together because of the gravity of all the galaxies that are in those clusters. So clusters of galaxies, the galaxies are all orbiting each other due to the mutual gravity of all the other galaxies. And we now think that galaxies have evolved over time because they merge, smaller galaxies merge to form bigger galaxies. So the reason why we have supermassive black holes in the centers of galaxies is that the earlier smaller galaxies had smaller black holes that weren't as supermassive, but as they merged, they would form the supermassive black holes would fall towards the center and they would merge, and the stars the orbits of the stars might get disrupted. It's actually very hard for stars to collide with each other because there's so much space in between the stars. So you won't actually see collisions of stars, but the shapes of the galaxies themselves might actually get really disrupted. And so we see evidence if we look really far back in time to the distant early universe, we see lots of disrupted looking galaxies. They aren't the same uniform shapes that we find in galaxies that are closer to the present age or that are closer to us. So yes, galaxies can definitely get disrupted. Okay. All right, so I'm going to answer in my own, non-expert way because I'm not a cosmologist. I don't do research in this area about, what happens at or before the Big Bang, and observationally, we can't observe before the Big Bang. The Big Bang defines kind of the start of the universe, and it turns out that it's actually not possible to observe even before about 300,000 years after the Big Bang, because it turns out that there's this wall of radiation that we can't see past. And so all of our knowledge of what happens before the Big Bang basically requires us to take our observations of the matter and energy leading up to the Big Bang, leading up to about 300,000 years before the Big Bang, and then running the movie backwards, using our knowledge of physics and our observations of what is in the universe, run that movie backwards and to understand what the conditions before the Big Bang or at the Big Bang were, or at the very first moments after the Big Bang. And so you might have heard about theories of everything, theories where the forces in nature, the electromagnetic force, the strong and weak nuclear forces, and the force of gravity, those are all separate forces today. But as you go to earlier and earlier times, and as the universe gets hotter and hotter, those forces actually merge to form, eventually we think, to form one kind of super force that the forces evolved from. And so there are a lot of physicists, a lot of smart people trying to figure out what those early conditions were, trying to figure out a theory of everything that explains how matter and energy and the forces evolved from the very early beginnings of the universe. And there's also this idea of, there's a concept called inflation that has come up, and unfortunately I don't have time to talk about inflation, but it's this idea that the very early universe expanded at immensely faster rates than has occurred ever since then. So it super expanded, and then the expansion slowed to the current rates. And so people posit the fact that inflation occurred because it explains a lot of certain observations about the universe today, even though we don't really know whether inflation is correct or not. But that doesn't stop cosmologists to start thinking about what might happen if inflation was correct. And so, even though I say that we can't know what happened before the Big Bang, if you assume that inflation, is correct, then and then you start extrapolating from these theories of inflation, it turns out that one of the crazy ideas that come up if inflation is correct is that inflation doesn't occur just once, but inflation can actually occur multiple times, and each time it occurs, a baby universe basically pops into existence. And this baby universe is independent of other baby universes that pop into existence. And so that's why if you think that inflation is correct, and if you think this particular model of inflation is correct, and if you think that this particular model of inflation also implies lots of baby universes being born, then that's how you can then have an idea of what happened before the Big Bang. And these baby universes basically imply that a multiverse can exist because each of these universes is completely separate from other universes. So you have lots of universes. So those are the crazy ideas that cosmologists are working on. And there are books out there that have been written for the layperson by actual cosmologists who try to explain this. So if you are interested in learning more, I encourage you to try and track down one of these books. But that's my quick answer to these two questions. And then before I forget, I'll just bring up the QR code again, and I'll be happy to answer any other questions that you might have from our presentation tonight. So thanks again for those of you who are leaving. Yes?
Just a quick comment. For people who want to look into the multiverse question, I recommend a book by Max Tegmark, Tegmark. He does a good job of listing a variety of different kinds of multiverses.
Yeah. So that's a very good suggestion. I hadn't heard that Max Tegmark had written a book about that, but it's not surprising. So again, Max Tegmark, Tegmark, has written a book about multiverses, or that talks about the different ideas behind multiverses. And what's interesting about him is that he is a cosmologist, but he actually quit cosmology, and he went on into neurosciences because he thought that he had reached the point where he could do all he could do with cosmology. And he couldn't do any more, so he decided to switch fields. All the more power to him. Yes.
Is the universe created, expand all the time because of the gravity exists, or universe create the gravity? Which one creates which?
So the universe expand because gravity exists, or did one create the other? So I'm not sure I am qualified to answer that, but from what I understand, the if you look at just the equations for general relativity, which is what Einstein came up with, you can actually, if you can posit or you can have equations create scenarios where you have universes that start off expanding, or they might be static, or they can start from zero and expand and collapse back into zero. And so these equations basically say that you can have universes exist in a lot of different ways, and you can even come up with universes that are totally crazy, meaning you can come up with a universe where you can fly out, and if you go along a certain trajectory, you actually go backwards in time, so that you can arrive back in the same point where you started off with, but in the past. So that's a crazy universe that doesn't correspond to anything that we are familiar with, but it's possible if you've use Einstein's equations and set some constraints and then derive what happens in that universe. And so what this means is that there are lots and lots of varieties of universes, most of them don't correspond to our universe. And why our universe started off and has evolved the way that it has done and is following this one particular pattern that Einstein's equations describe, and not some other crazy pattern, I'm not sure anyone can say. So, so that's probably as best as I can explain it, the way that I understand it, which again might be completely meaningless to anyone else in the audience. Yes, in the back. Boy, I'm not sure I can answer that either. Yeah, the laws of thermodynamics work for closed systems. And so they actually don't, the way that I've heard it explained is that they don't really apply for the universe as a whole, because the universe can't be described as a closed system. And so, so one way to think about that is that, because the universe is expanding, where the box where you are describing things are happening, that's not constant over time. And so, basically, if you're using the laws of thermodynamics to try and find constraints for what can and what can't happen, you really can't do that for the entire universe. Does anyone have questions about any other thing other than cosmology, which I might be able to answer? Yes.
So back to the dark energy finding from the DESI paper, you said something about it being based on their theory of dark energy. So when they're showing those contour lines based on the observations, are those observations resulting in the W0, WA, that's coupled to their model?
So I think what I was talking about was this paper, when I was saying that there are particular theories. So if you look closely, so this observation can be explained by the Axion dark energy model. So they have their own pet theory called the Axion dark energy model, and I don't know enough about this particular subfield, whether they are the only people who promote that model, or whether there's an active community of researchers who are writing papers about axion dark energy, and their particular model is just one variant of that. But so basically, they are saying if their axion dark energy model is correct, then based on this paper, this preprint, which is again not been peer reviewed, so it's still being reviewed. They started writing this after the original data release of the DESI results. So they have been working on this for months, but they have probably been working on their axion dark energy model for years. And other people have been working on their own personal pet theories of dark energy for a long time as well. So I'm sure that as time progresses, as more and more theorists latch onto these new observations, they will be publishing their own papers about what the lifespan of the universe might be. So so don't count on this as being absolutely correct, because there are a lot of assumptions that go into the results of this paper.
The contour plot one, that is peer reviewed?
Yeah. So this does come from a peer-reviewed paper, and yes, so you can have more confidence in this than on that other paper that I showed.
Okay, cool.
Yeah. Yes. Hmm. Yeah, that's a really good question. What is going on with the center of the universe, and the short one-sentence answer to that is that there is no center of the universe. Okay, and the longer answer, and this is somewhat complicated, is that when we and this is a misconception that happens when we talk about the Big Bang, just from the words Big Bang, because if you think about it, that implies, and if you think about even the ways that I've described it, it sounds like this is just an explosion, right? And when we think of explosions, we think of, like a bomb going off. And if a bomb is going off, well, there's shrapnel that flies off and goes off in lots of different directions, but that implies that there is a volume of space in which the shrapnel is flying. So if a bomb goes off, there's some pre-existing room or volume where the bomb exists beforehand, and then all the pieces of the bomb fly off into that pre-existing space. So the problem with that analogy is that it doesn't correspond to what's happening with the universe. So in order to really understand what's happening with the universe and the Big Bang, is you have to go back to Einstein's equations. And so in Einstein, the universe is described as a four-dimensional space-time. So you have the three dimensions of space, and we're all familiar with that, but time is that fourth dimension, which seems, it's hard to imagine, to understand what a four-dimensional space-time looks like. But according to Einstein, that four-dimensional space-time is all there is to the universe, meaning there's nothing that the universe is expanding into. So if the universe starts out very much smaller, that's all there is. It's that very much smaller four-dimensional space-time. And then as it expands, that four-dimensional space-time gets larger, but it's not expanding into anything that's also larger. So hopefully that sort of makes sense. Now, where it gets really, really confusing and where it might break your mind is that, according to Einstein again, depending on how you set up your model of the universe might not be finite. It might actually be infinite. And so what that means is, well, if you have an infinite universe, and what does it mean if the universe started off as a point and it, at the Big Bang? Will it still be infinite? And where is it expanding into? Or how is it getting larger if it's already infinite? Well, this is where one of those cases where the mathematics kind of works out, but it doesn't really make any sense to us, like, as ordinary beings who live in a three-dimensional world who don't understand four-dimensional space-time. So that's kind of, in a roundabout way, the best way that I can explain it, that there isn't a center to the universe. And one way to think about it is that everywhere, anywhere in the universe is as good of a definition of where the center is as anywhere else. So if you're looking at, what the conditions were very early in the universe, you can really go anywhere in the universe and say, if you, look at the conditions here in the universe and run the movie backwards in time towards the beginning of the Big Bang, that's what, and then compare that to anywhere else in the universe, those points should all look very similar or almost exactly the same, no matter where you are in the universe. Hopefully I haven't confused you even further. Yes?
Can we assume if there is a multi-universe, so our universe could be a baby of an existing universe? Instead of calling it Big Bang Theory, that there was universe, so our universe, if we believe, if say we have there is multi-universe, so our universe started as one of these stars, so we can call it the Big Bang, but now we are a new, we are not only universe.
Yes. I mean, I think if you read, one of the popular descriptions of how the sort of inflationary cosmology works that leads to multiverses, they sort of say what you're saying, because one of the ways that inflation works is that inflation doesn't need, because it's a quantum mechanical process. So quantum mechanics, you don't need a cause for something to happen. Things can happen spontaneously. And so what that means is that if you wait long enough, and if inflation is correct, and inflation is a quantum mechanical process, you can have universes pop up, inflate out of nothing, and because they're inflating faster than the speed of light, they actually end up kind of sealing themselves off in their own pocket universe, and that's why they end up being a separate universe. And so that's basically how these multiple universes come into being, because inflation as a quantum mechanical process doesn't need a cause, and so it can happen anywhere at any time. And if you have an infinite universe, that means you can have infinite numbers of pocket universes popping into existence in that universe. And each of those pocket universes or baby universes can lead to their own inflationary sets of baby universes. So yeah, I mean, you basically have infinitely huge numbers of baby universes pop into existence if you assume that inflation is correct, or that particular model of inflation is correct. Yes?
Is it possible that our galaxy, or maybe our universe, I didn't read it, my professor sent it to me, that we're inside a black hole? And how would we know?
Yeah, that I'll defer answering that, because I've read some things about that, but I don't think I've read enough to where I understand it enough where I can then explain it. So I'm gonna decide not to answer that.
Can I skip over to I3 Atlas then?
Sure, but I haven't really followed up on that other than knowing that it's out there, that it's another interstellar object, and that it's get brighter, and then it's going to be heading out away from our solar system sometime next year. And then maybe one other thing I'll say about it. I mean, lots of astronomers, people who study comets, are observing it and learning lots of things, which I haven't kept up with, so I can't tell you anything that's happening about what people have learned about it. But if you remember, the cometary object Oumuamua was discovered about 10 years ago, and since that time we've had 3 objects that have been discovered that were that are these interstellar comets that originated from outside of our solar system. And so that's really exciting because it sort of says that there seems to be a pretty good sized population of these objects. But I think also what's really exciting is that the Vera Rubin Observatory, which went online earlier this summer, it's expected to find, I think they're estimating, on the order of maybe, I can't remember if it's a couple dozen over the lifetime of the survey, which is about 10 years, or whether it's, so that I think that's correct. Maybe 20 or 30 objects. So that means you'll be finding a couple objects a year. So we'll be, hopefully immersed in lots more data about these interstellar objects, comets. Yeah, we're just only noticing them now. All right, it's 8:30, so I guess you still have time to go up and see the elephants. So thanks, everyone, and we'll see you next year.